And all of this recording is actually going to my compact flash card. It's not saved on the hard drive of this computer. I'm streaming everything to my compact flash card. So this way I can take it home and upload it later. All right. Okay, the biggest complaint about the virtual machine is it is way too slow. It is so slow that Xorg will time out the detection of video cards. And that's why many of you have problems running the GUI. Okay, it starts up and then it goes away, and then it starts up and then it goes away, and then eventually you get a black screen saying that Xorg has failed to recognize a usable graphics card or something to the same effect. And that's why, because it's running too slowly. Now, partially it is because some of you have thumb drives that are not intended for running virtual machines out of. In other words, your flash drive is too slow as well, which is compounding that with the virtual machine. It is just way, way, way too slow to get it to work. So what we'll do today is we'll find out another way to run the same thing, except this time we'll run it without the GUI. Okay? And I will go through the whole cycle for anyone who could not possibly get into the GUI in order to create the persistent drive. We'll do it today, all from the command line interface. Okay. Does everybody understand what I'm trying to do today? Okay. At least for the first part. We'll see how long it takes for this part. Now, one thing I will do today is I'm going to shortcut some of the stuff here. So instead of testing the virtual machine step by step, I'm going to go a few steps at a time so that we don't waste too much time doing this. I will start with I'm going to start with creating the image file first. And this part is done in Windows natively. So I'll open up a window here and then run qemu-img. The command is create-f to specify the format. It is qcal2. I think qcal2 is the default format already, so if you don't specify anything, I think that's the default, but I'm not 100% sure. The name of the file, that would be my image file. And was it with this class that I created a drive that was too small? No? Okay, it must be my... yeah, 2 gig would be way more than enough, for this purpose. But we'll just go ahead and create a quote-unquote 2 gig disk image file. And in Windows Explorer, you can see that that file is now here. It's only 193 kilobytes because it's in qcal2 format, which means if you're not using that portion of the virtual disk, it does not take up any storage, which is nice because otherwise I'll have a 2 gig file sitting around here, which is fine. I have a 16 gig drive, but I still don't want to create big files unnecessarily. All right. So at this point, I can create the batch file to start up everything, and we'll say new text file, and it will rename the file to vm.bat. Now, if you're experimenting with the virtual, with the emulator, you can potentially create multiple batch files just so that you can test what each feature would do. Okay, so here is the important part. Okay, I'm glad that Notepad remember my old setting, which is a really large font. Okay, so -L BIOS is needed because the emulator needs to know where to find the BIOS files. Now, if you have installed QEMU 0.9 something, you do not need to specify this line because the BIOS file is in the same folder as QEMU itself. So this is only needed if your BIOS folder is in the subfolder. The BIOS files is in the subfolder called BIOS. -M512, I'm giving the virtual machine 512 megabytes. -CD-ROM, /dev-live.iso. This is where I put my ISO image. -HDA, I have an internal hard drive, quote-unquote internal hard drive, which is provided by the image file called disk.qcal2, the one that I just created. -bootd, which is one thing that I forgot to mention, and some of you figured it out anyway. This way, the BIOS knows which drive to use to start up the virtual machine. Because once you have 2 drives, the CD-ROM and also the internal hard drive, the BIOS would actually use the internal hard drive to try to bootstrap first. and it won't even look at the CD-ROM in that case. So you have to force it to use the quote-unquote D, which is the CD-ROM drive. Okay, more stuff to come. -net. Okay, now this part we did not specify earlier, but I'm going to put it in here. Make VLAN equals 0. This part, I'm just going to highlight the part before I talk about it. This part is telling the emulator that we want a virtual network card with the virtual machine. Okay, so it's quote-unquote plug in a NIC card to the virtual machine. If you want multiple NICs, you can actually say -net NIC, VLAN equals 1, and so on. You can actually have multiple network interface cards installed on your virtual machine. So if you want to test, a router or something along that line that requires at least 2 NICs, you can actually do it inside the virtual machine. But in this case, we only need 1. The next one is -net user. Now this one is basically saying, with the NIC that we have just installed, how does that NIC inside the virtual machine connect to the outside world? User is quote-unquote the user mode. It's kind of like a lazy mode. It's using the host operating system as a bridge to get out to the internet. In other words, if you have a Wi-Fi card and your host operating system is working just fine, you don't have to install a Wi-Fi driver inside the virtual machine because the virtual machine is going through your host operating system to get out to the internet. Okay, so this is really cool for the most part. And this part is what we need when we run the virtual machine in text mode, which runs faster. We are forwarding certain network traffic to the virtual machine. Now this part is the part that makes it a little bit harder to read, and I will explain what it means. Okay. Host forward instead of guest forward means the host can initiate a connection that is intended to reach the virtual machine. Okay? In other words, you can now run PuTTY, WinSCP, FileZilla on the host side in order to connect to the virtual machine so that you can open up terminals, okay, PuTTY terminals. You can also transfer files using WinSCP. Okay? We are forwarding TCP traffic instead of UDP traffic. It's empty here, which means it doesn't. We are not specifying a particular interface. An interface is like 127 localhost and stuff like that. We are forwarding port 2222 on the host side to port 22 on the guest side. Port 22 is what we use for SSH. In other words, if you want to open up a PuTTY connection, which is a SSH connection, we need to open up port 2222 on the host side in order for that to end up on port 22 on the guest side. We're building a wormhole. You guys are not. We're building a wormhole to breach the 2 universes. The outside universe is the host environment, and the other universe is the guest environment. So we're building a wormhole. On the host side, it is known as port 2222. On the guest side, it is known as port 22. Now, it may seem like this is a one-way wormhole. The one-way part is only determining who gets to initiate the connection. Once the connection is established, it is actually a two-way connection. So you can get stuff in, you can also get stuff out. It allows your host operating system, which is Windows in this case, to communicate with the guest operating system, which is Linux. Okay, so we'll come back to this part and see how we can actually use this later on. Are we doing okay so far? Am I turning this into a networking class? Yes?
Just wondering what's the significance of actually using the 2222 and 22?
You can choose anything you want, with the first number. You just have to remember what number you pick. Okay. You can choose, 2220, 2020. Okay. Any port that is not used, you can use. But I wouldn't use port 22 because anything less than 10,024 is a protected port, and the operating system will not let you do it. 2222 should be fine. I've used this number for many years. So unless you have another application using up this port, this should be fine. All right. And then we have some more. -USB, -USB device, tablet. Now this part is strictly for convenience purposes. In other words, I don't want to have my mouse cursor stuck inside the emulator console, so I have to press Control Alt all the time to get out of the virtual machine. This allows me to move the cursor in and out freely without getting locked up. Okay, so it's completely optional. So now we are done with the command line. It's kind of long, but it's I explained every single component, and I can upload it to Moodle too once it's all done. But I wouldn't do it until I know it works, right? All right. So how many of you think that it will work the first time? I'm not raising my hand. Okay, I have no confidence in details like that. In myself, dealing with details like that. So far, so good, but we don't know yet. Okay, this part is important. We don't want to run the GUI because that's taking a long time, and that's the part that will always fail, making the virtual machine basically useless when you try to use it inside Windows. So what we'll do is we'll pick live persistent. It's not important at this point because the persistent drive has not been set up yet. We'll press the tab key. Okay? When you press the tab key, it displays the parameters or arguments that is passed to the kernel to tell the kernel, do this, do that. Oh, by the way, you want to do it this way and that way. Okay? So you can see persistent is one of the words to tell the kernel that it has to go find a persistent drive. So there are other, no prompt means, it's not going to, give you a whole lot of questions, as it starts up. But we're going to add one more item. We'll press the space bar, and then type text text. Okay? This is what tells the kernel and say, don't even try to start up the GUI. So we are going to we will run the virtual machine in text mode only in this case. It will still take quite a bit of time to start it up, but much faster than having the GUI to run, and at least it will run. Okay, because with the GUI, it won't even run. Okay. Press the Enter key. It starts up. It's a little slow. So we'll give it some time to start up. And as it starts up, I'm going to get into Firefox to get some more tools that I will need later on. I will go to the power server, which is power.arc.losrios.edu, and go all the way down to this part here. I want to use PuTTY, so right-click and save link as, and then I'll put it into the same location where I put everything else. In this case, I will put it into my Windows F drive. Go to VM, go to QEMU, and save the file over there. PuTTY is a SSH client program. In other words, if you have another computer running an SSH server, then the client program can make a connection and open up what we call, simply called a terminal to the other computer. Now, it is not strictly required because you still have the QEMU console. The problem with using the QEMU console is there's only one. So you have to do all your programming, your man page, your debugger, and everything in one single screen, which you can do, but it's not very handy. It is much more handy if you can open up multiple terminals, one stuck in a man page, one stuck in an editor, and one for debugging. Yep.
Why don't you just use all the function keys to open up different virtual terminals?
Yeah, but then you can only display one at a time. You can use the utility called screen to break up the screen, the actual physical screen, into subportions, but then you have smaller characters. So PuTTY is still a very useful tool to have. All right, so that's the first one that I download. And then the second one is called WinSCP. Professor Carol Lever called this Winscape because it spells kind of like Winscape, WINSCP, but it really is WinSCP. SCP stands for secure copy over the network. Okay, so it's kind of like a tool for file transfer. Look at it as FTP. So I'm going to do the same thing here. Right-click, save link as, and then put it into the same folder where I have my QEMU. So now I have all the utility programs that I need in order to access the virtual machine in the same folder. Virtual machine, see, okay, it's getting there. Almost sounds like one of those infomercials with cookware. They would do something and then go back and check. I'm hungry. Okay, they would go back and check the steak or the chicken and say, "Oh, it's almost done." Actually, it's already done by the time they put it in the pot, right? Yeah. I also like those cleaning products. Being able to clean all kinds of dirt and grime and whatnot. I'll bet you if they use the finger and just to do it like this, it would clean it all up too. There's no need to use a steamer. All right, so we're getting there. The network card is getting connected, or not. We'll give it a moment. Any questions up to this point? No questions? Okay. We don't really need the network up to this point, so this part is not absolutely needed, because the first thing we have to do is to partition the virtual hard drive and make our persistent partition out of it first. This time, okay, it's all done, but this time we don't have gparted. We cannot just click and say, oh, I want to create a partition of extension 3 and so on. So we're going to do all that using the command line interface. But before we go there, let's try PuTTY. How many people know how to use PuTTY already at this point? Okay, some people, very good. Okay, for those of you who have not used PuTTY before, double click it. It's basically kind of like Telnet, except it is more secure. And this screen will pop up. If you want to connect to a virtual machine, what you need to do is to specify localhost as the host name, and then use port 2222 as the port number. Okay? And then you press open. If everything goes okay, all right, we can log in as, I can only log in as the regular user at this point because I have not created a custom user at this point. All right. Now the nice thing about PuTTY is you can open up as many as you want. You can say duplicate session, and then it will open up a second one. You still have to log in as user, but now you can open up as many of these terminals as you want. The second thing that is really good about PuTTY is you can change the font size. For classes, I can change the font size to become a little bit bigger so that people in the back can see what it is, to see what I'm typing. So you go to change settings, go to appearance, and then go to font here. Change the font, and you can change even what font you want to use. I like Terminal a lot, and use a 12 point. Apply. And you can see that this is really kind of big. Okay, so that's nice. Now on the other hand, if you're running PuTTY on your laptop computer, and let's say you have a 12-inch or a 13-inch laptop computer with limited space, and you want to open up at least 4 PuTTY sessions all at the same time, you can choose a smaller font, as small as your eyes can comfortably handle. That way you can display more text, more help, and you can look at the debug screen more conveniently using a smaller font. Okay, and you can customize everything and then save your settings. So if you go back to PuTTY, let me go back to change settings here. I can go back to session here, and if I want to save this one as a special session, I can save it as cisp310 and then click save. So all the settings that I have modified will now be saved as the cisp310 session, which comes in pretty handy. Okay. Any questions at this point? No questions? All right. So let's go ahead and do something dangerous to the virtual machine. I'm not doing anything dangerous to the Windows box here. Let's go ahead and try to partition the hard drive and then format the hard drive that we have just created. I cannot do it as the regular user. I have to change to the super user. It's not. That one is kind of stuck, I know. Maybe it's because the configuration screen is still there. Yep, there you go. Okay. password is root ball, and the program is called fdisk, which is the same name as in DOS. When you say fdisk, you have to tell it, which disk am I dealing with. In this case, it is SDA, and you can use P to print out, the current information that we know about that particular drive. There's nothing there, not even a partition table at this point. So the first thing we have to do is to create a partition table. M stands for menu. It will show you all the available options. One of the available options is O, to create a new empty DOS partition. So that's what we'll do first. O, and it will complain a little bit about stuff. That's okay. And then it will use N to create a new partition. It will be a primary partition, the first one, and for the first sector and the last sector, we'll just take the default. In other words, we're taking the entire hard drive as our partition, our persistent partition. When it's all done, press W to write back the changes, because up to this point, no changes have been made to the hard drive. Okay? Until you say W and press the Enter key, no changes has been applied. When you press the Enter key, it will confirm that all the changes have been made, and then it will actually get out of fdisk. The next thing we have to do is to format the hard drive. The first step is really just to allocate which part of the hard drive do we want to allocate to this partition, okay, and what type of partition it is. But we have not formatted the partition yet. So now we can format the partition. The command to do that is mke2fs make extension to file system dash lowercase j to specify extension 3, and then you specify the partition, which is /dev/sda1. In Linux, SDA1 means the A means the first internal hard drive. The next one will be B. Your external drive would typically be E, F, G, H, and so on. And then the 1 here means the first partition of that drive. If you have multiple partitions, the next one is going to be 2, 3, 4. And if you have extended partitions, it will be 6, 7, 8, and so on. Are there any questions up to this point? No? Okay. You press the Enter key. It's going to do its job, formatting the hard drive to extension 3. And I forgot one thing. I think I can do it later. We'll see. I forgot to label the hard drive to LIVE-RW, which is also very important. If you forget that step, it's not going to recognize it as your persistent drive. So I'm going to look up, I'm going to cheat here and look up all the stuff that has a label in it. And it's, well, not too much. E2 label. I bet you E2 label is what we need. Extension to label. Since I don't know exactly how to use the command, I use man to help me. So the man page or the manual page sets E2 label, and then we have to specify the device, which in this case is /dev/sda1. That's the partition. And then we have to specify the label, which is LIVE-RW. You can see how useful the man pages are. Basically, if you can remember which command you need to use, you really don't need to remember all the details of how to use that command. So we'll go ahead and run E2 label /dev/sda1, which is the partition that we have just formatted, and then give it a label, which is live-rw. And it's all done. All right? Any questions at this point? No questions? All right. So we'll go ahead and tell it to reboot. Actually, I will ask it to power off, which is the command to turn off the virtual machine safely. And then I can close all the putty sessions because it's all going to stop working anyway when we shut down the machine. Are there any questions up to this point?
So you didn't power off the terminal and you just powered off the whole machine?
Yeah. Because I have to reboot it in order for the persistent partition to become effective. All right, let's check. It's almost there.
It's just that we're still in Windows and the OS on, move the disk.
I'm pretty sure there's a way to do this without having to reboot the machine. we'll start it up. And I'm going to use this to go to. Well, let's try to do our homework. Remember our homework assignment, how to use Linux basically. So we'll do it once in this environment, because there will be some questions like, how do I copy and paste instead of retype everything? Someone says there's an iPhone 4 app. If you put the app next to a keyboard, it can kind of guess which keys you are typing on the PC keyboard that is placed next to the iPhone 4. It doesn't work with iPhone 3 because the sensor is not as quick or as the frequency response is not as good with an iPhone 3, but with the iPhone 4 sensor, it can actually do it.
Why would you want that unless you're trying to get somebody's password without them knowing about it?
Well, it's going to be easier to do.
Well, like the CIA, NSA, people like that will use that kind of stuff. But it has to be really close to the laptop.
I can't
Well, with certain government agencies, they can just beat the crap out of someone until that person gives up and say, okay, my password is.
There's more KGB than CIA.
It's cheaper that way.
All those places don't let you bring a cell phone through the front door.
All right, we're getting there. It will still say that it's starting GNOME, but then it won't actually start it because the startup script of GDM would actually recognize the kernel flag of text and not to start up the graphical user interface in this case. All right, so we are slowly getting there. And I'm going to get into my homework assignment first. Oh, not that one. I don't think we are getting back to cisp310. Does anyone think that you want to get back to cisp300?
No.
No?
You get extra credit for doing
I knew somebody's going to ask that question.
Yes.
The question is, what if you can't pass that class now? All right, so this is our homework assignment, and for the most part, everything is pretty easy to do, but I'll just go through everything. Oh, I forgot to specify text, did I? Okay, now, it's okay to start a GUI, but I don't want to wait until the whole GUI thing is finished. So I want to switch back to the text mode in the virtual machine. The way to do it is Control-Alt-2 in QEMU will bring you to what we call the monitor of QEMU. And in here, you can send key Control-Alt-F1, which is typically the key sequence to turn into the text mode in any Linux environment from a GUI. So after that, you use Control-Alt-1 to switch back to the normal screen, and now we are back into the console screen. QEMU actually can do a lot of stuff that we are not even going to explore in this class. I just have to wait until the network is up, and I can do everything else in PuTTY. Because the most common question is going to be, now, since I have the code already here on the web page, how do I copy and paste it into the virtual machine so that that becomes the starting point of homework assignments? In this class, especially at a later stage, most of your homework assignments will start with a C program. So it will be helpful to be able to copy and paste some code from Windows into the virtual machine so that you can start with that homework assignment. And this is still taking its time. Go ahead and start up PuTTY without connecting to it. Oh, here's the other thing. when you load, it actually remembers the host name and everything else. So that's the other nice part about using a session inside PuTTY is it saves all the settings for you. Okay. All right, we're here. All right, so I'm going to log in as root first. In order to create my user account, remember you have to create an account based on your last name. So that's add user. I don't use SU anymore because I directly log in as root. You only need to use SU when you log in as user. Then you have to change your user as super user. So that's why in this case I don't need to do SU. Add user Anya. Give it a password. And now we have the user account Anya. Yep.
When I was running it from the GUI, and it told me that you can't log in as root from the GUI. You have to first go in as...
That is correct, because you don't want to log in as root. That's the problem with Windows. Because in Windows, especially with home editions of Windows, the default user is actually a system administrator. Okay, so what do you do, or what do you think most users with the home edition of Windows would do? They go online, they browse the web, they go out, right? And if they get infected, if they step on some malicious code, the malicious code can potentially run as administrator on the Windows side, and then you get the system infected. That's why in Linux, they try to discourage people to do anything as root unless it is absolutely necessary. Because if you are a regular user and you step on something, yes, your account can be compromised, but it'll be much harder to compromise the system as a whole. So that's why you cannot log in the GUI as root, because it's a security thing. It's to make sure that you cannot browse the web and do other stuff as root.
So that's just for the GUI.
That's just for the GUI. Yep. You can start up most commands inside the command line as root. Okay. All right. So this part is done. I think that's all that I have to do as root. One more thing, run mount so that I can confirm that live cow. My mouse pointer doesn't appear inside here. You can see that live cow here is mounted on /dev/SDA1. That's confirmation that my persistent drive is up and running. Are we doing okay so far? So I'm basically redoing my homework assignment, but this time based on a text interface instead of a GUI. All right, so if this is all good, I can now go here, open up a PuTTY session, log in the same way, except this time I log in as my username, my new username. All right, now I can do my homework. To do my homework, there's a whole bunch of copy and paste, remember? If I'm lazy enough, I can even copy and paste these commands, right? It takes me more time to position the mouse pointer to copy and paste it. All right, here's the question. I have just copied the text into the clipboard in Windows. How do I paste it? Right click, exactly. Right click on PuTTY will paste whatever you have already placed in the clipboard as if you just typed it, okay? So because I'm so lazy, I just do this all day long. Create the file, okay, fine, copy. This time I have to use cat. Remember the trick? You copy everything that you type on the keyboard to the file that we are creating, which is simple.lowercase_s. Right click, Control D. It looks kind of ugly with all the empty lines and stuff, but as long as it assembles, it's not a big deal. This doesn't look right to me. Does it look right to you?
No.
It looks exactly the same, except this is wrong. It will crash. Let's see, will it crash? No, it doesn't crash. It doesn't crash. It will just come back with an error code. Okay, so it's okay. We'll just do it the way it is right here. So I'm going to do a ls-l to confirm that this file is successfully created. Okay, it's all good. And long commands like these, I will just copy and paste it to. Now you can also copy and come on. Okay, there we go. Paste. This is why people forget how to do stuff, because they just copy and paste too much. And then even that I can copy and paste. And to turn in the homework, more copy and pasting. There we go. And the file is created where? Where is the archive actually created?
The home directory.
The home directory. That's right. And that's why it is not here. Okay, because I'm not in the home directory. I'm one level down from the home directory. Okay? So but if you go back out to the home directory, it is there. But now we have a problem. This is the virtual machine, and it doesn't have a browser. So if you want to turn in your homework assignment, you have to copy that file out to Windows first, and then from Windows, you can use your favorite browser to upload it to Moodle. Okay? So, multi-step process at this point. So the next program we have to use is WinSCP. WinSCP is actually, you can actually see the interface is very similar to PuTTY. Come on, start up.
You're really trying to make people hate Windows.
You could use a text browser too. You could use a text browser as well.
A text browser, like links.
They work.
Does it maintain keep track of cookies? Can it deal with HTTP?
Can.
Okay. Why is it not starting up?
Forever. On a site basis.
Oh, there we go. Finally, we got it. All right. So you can see this interface looks kind of familiar because it's the same or very similar to the one that we have in PuTTY. So once again, you can save your session to save yourself some time. Host name, once again, is localhost. Username is your last name. Password, whatever you choose. Port number is 2222. And at this point, I can save the session. And you can change the name of the session. I'll just keep it the same way as it is suggested here. And then you click login. They ask you for the password again. I don't know why. Maybe I type in
the box check.
Oh, okay. All right. So now we have the interface to copy files between the host and the guest. Basically, it's really just between the SSH client and the SSH server. We can see the file here, test.tar.gz, and then we can just drag and drop and put it into my documents folder in Windows. Copy, and it says I already have one there. It's okay, go ahead and overwrite it. So now we have a new file over here. And if I go back into Windows, let me go back into my browser. Let me change my role to a student so I can turn in my homework assignment again. So switch role to student. Go back to the homework assignment. Scroll all the way back down here. Go to my documents folder. Test.tar.gz. Upload it again. The old files in the upload area has been deleted because the new file is there. It is there to replace the old file. Continue. I'm done. Okay, so I have just illustrated how to do your homework assignment from scratch, and I mean from scratch, minus installing the Windows part. So, any questions? Yep.
How are you grading these? Are you going through a program, or are you doing it by hand?
I have a program to do it. Anything that I can automate, I have a program to grade it. And that's why it is so important that your home directory is based on your own name. because otherwise I cannot tell who turned in the file. At least the script cannot. Then I have to go in and look into the file to see if there's any comment about the name.
So we need to have our stuff exactly in the directories as specified, correct?
Say again?
We need to have all of our files in the directories that you specify
Yes.
exactly.
Yeah, the structure of the folder has to be fairly rigid. Yep. Any other questions? No questions?
Just curious question. How
Go
would
ahead.
you get our names if there is just simple? Like simple O, simple.
Because your name is inside the path. Your account name is your last name. And the tar file captured your account name. So that's why I can easily tell who turned in what. Okay. Any questions at this point about all this stuff? So I think this will work. Okay, the text interface I think is far more usable compared to the GUI environment. Any questions before we move on? Nothing? No questions? All right. So now we go back to binary numbers. Okay. How many people actually finished reading the binary number addition and subtraction part? 3. Okay, well, at least I appreciate the honesty of the rest. I can actually tell, who has read what, because Moodle allows me to generate reports, based on that. It doesn't change your grade, okay? Whether you read the material or not really does not change the grade by itself. But I think if you read ahead of time, it will make the material easier to absorb in the class, and that's why I encourage people to read the material before the class. All right, so let's go ahead and get into this stuff. Okay. Last time we talked about binary to decimal conversion. The other way around. We talked about decimal to binary conversion. And I used an example, and I told you guys if you know how to make a change, and work in a fast food store, you know base conversion already. In fact, you know something that's more difficult than base conversion. You remember that? The $half thing? Okay. So this part is done. Okay, the base conversion itself is done. The next slide. Oh, I also mentioned base 16 to base 2 conversion. And that's also very easy because 16 is a power of 2. And that's why you can use that trick and just use a lookup table to look up, this is one hexadecimal digit, base 16, and this is the 4 bits that it's representing. Or vice versa. You can look at 4 bits and say, oh, these 4 bits can be represented by this particular digit in hexadecimal, and it's just a table lookup thing. There's no division involved. There's no multiplication involved. It's just easy. Okay. Does that explain why we have hexadecimal numbers in computers, especially low-level programming? Do you guys learn about hexadecimal numbers in C in your CISP 360 or equivalent class? No? They never taught you the 0x prefix to write hexadecimal numbers? Only some? Okay, so I can see some instructors, presented that and some do not. It's a really nice thing to do, because now you can have a different representation of numbers. You can actually write numbers in hexadecimal, which is very handy in assembly language programming. All right, the next slide talks about adding. Okay, how do we add 2 binary numbers together? Well, there are only 4 possible cases. 0 plus 0 equals 0 with no carry. 0 plus 1 is 1 with no carry. 1 plus 0 is 1 with no carry. 1 plus 1, well, you can call it 1, 0 in base 2, but I would call that 1 plus 1 is 0 with a carry. Okay? Because that's how we can have multi-digit addition. So let's go ahead and review addition. And I mean addition. Base 10 in this class. You guys would say, are you insane? This is not kindergarten. Well, but I'm going to explain it in a way that will make the mechanism also usable in base 2 addition. So we'll start with something that we know already. Remember, I'm used to Linux and not Windows, so all of this stuff is kind of foreign to me. How to start a notepad and stuff. All right. Let's think about how to add two numbers. Like, let's try 4, 5, 7, and we'll add 128 to it. Okay. All right. Base 10. These are base 10 numbers. 7 plus 8. Well, it's more than 9. So how do we represent 9? I mean, a value that is more than 9 in a multi-digit addition.
You transfer one number over.
Okay, you're talking about a carry.
Yeah.
Okay. So the way the way we usually write it, by hand, is we put a little 1 on the next column. Is that the way you were taught?
Yeah.
Okay. That's the carry to the next digit, so that when we add the next digit, we remember there's a carry. Well, since I'm using a text editor here that has a fixed size font, I cannot really do the subscript and all the fancy stuff. So what I would do is I'm going to use one more row just for the carry. Okay? In other words, the first row represents the result of the addition. The second row represents the carry from the previous digit, the less significant digit. What should I put here? A 0, because there's no less significant digit. This is already the least significant digit. All right, that's pretty easy. What do I put here? 7 plus 9 is 5 with a carry to the next digit. Is everybody understanding, how I'm using this? If I have to annotate this, I can just say this is the carry from the previous less significant digit. This is the result of the addition. Is that okay? Okay. All right. Now what is 5 plus 2? 7. And does not generate a carry, so I leave it blank for now. 7 plus 1 is, let's finish the first one first. Okay. 5 plus 0 is 5. And then 7 plus 1 is 8. Now, in this case, 5 plus 2 does not generate a carry. 7 plus 1 does not generate a carry. So this carry is a 0. Does it make sense?
Yep.
Now, most of the time, when we actually do it by hand, we don't write the implicit 0 as a carry, because it's just one more step that is unnecessary. But in this case, I want to represent the carry from the previous digit, whether it is a 1 or not. So this way, it is more explicit. And then we have 4 plus 1 equals 5. 5 plus 0 is 5. And there's no carry to the next digit, so I don't need to do any leading 0. I don't need to write that 0 out, because it would just be a leading 0, which doesn't really change the value. Is that okay? The process and how I use one row just to represent the carry from the previous digit. That's the most important part. Is that okay? Now let's do it in binary. Okay. First of all, let's go through a quick exercise so that you can practice your base conversion, routine thing. What is 13 in base 2? 13 in base 2 is 8 plus 4 plus 1. So that will be 1, 1, 0, 1. Okay? You can do it, just like I do if you have done it like for the past 10 years or so. Okay? Now this is base 2, so at least at this point I would use parentheses 2 to indicate this is not a decimal number. And we'll go ahead and add, I don't know, let's try 9. Okay? What is 9 in base 2? It's 8 plus 1. This is 8.
1, 0, 1.
This is 4. This is 2. This is 1. Okay. The same way, I'm going to use one row to represent the actual result. I'm going to use another row to represent the carry from the previous digit, and then the last row to represent the actual result after the entire addition. All right. This is going to be a 0 because this is the least significant digit. There's no carry from a less significant digit. Is that okay? Same trick that we did earlier. 1 plus 1 in binary is what? It's a 0, but it has a carry. So immediately we put a carry here. Then we have 0 plus 0, which is 0. 0 plus 0 is 0, does not generate a carry. 0 plus 1 is 1 without a carry. So that means this is just a 0. 1 plus 0 is 1. 1 plus 0 is 1 with no carry. 1 plus 1 is 0 with a carry. 0 plus 0 is 0. And this last one is just going to be here. Okay. Now, let's go ahead and double check to see whether this result is actually right or not. This is a binary number. What is it representing in base 10? What is the value that it is representing? Well, it is, this means that's 0, 1, 1, 2, 1, 4, 0, 8, and 1, 16. 16 plus 4 is 20, 20 plus 2 is 22. Is that right?
Yeah.
Okay, so that's double checking. And also a chance to practice base conversion. There will be no questions in the test about base conversion because I know you guys have super duper calculators. If there's any type of base conversion, it's going to be converting to obscure bases like base 7, base 9, that sort of thing. Something that your calculator cannot handle. All right. So are we okay with binary addition? It's all good? All right. So getting back to the notes, just so that we can relate what we have just done. You have seen this already. This is just more tedious, more steps. Okay. Any questions about this part? You can see that I ran out of patience, in the last few digits and just kind of jumped all the way to the end.
What's plus C? What's plus C?
That's the carry.
Ah.
Yeah, I used the C to represent, this row represents the carry. Addition is done. Let's talk about subtraction. Subtraction is kind of easy too, for the most part. 0 minus 0 is 0. 1 minus 1 is 0. That's regardless of which base we are using. 1 minus 0 is 1. Okay, so all these three cases are easy. The only one that is a little bit difficult is what is 0 minus 1? 0 minus 1, one way to look at it is just negative 1. Negative 1 in base 2 is negative 1. But the other way to look at this is 0 minus 1 is 1 with a borrow from the next digit. Just like in base 10. So let's go back to our notepad, and this time we'll do a subtraction in base 10. Okay, so we'll go ahead and do a 900 minus 11. And this is all done in base 10. Same thing, except this time we have a borrow to deal with. So this row here represents the borrow from the previous or the less significant digit. Just like before, the least significant digit of the number has no borrow because there is no less significant digit, or they're all implicitly 0. So we are not borrowing. There's no one to borrow from this particular digit. All right. 0 minus 1 is 1 with a borrow. 1 minus 0 is a 1. Oops. My bad, I'm mixing different bases. Scratch. My bad. This is base 10. Okay. 0 minus 1 in base 10 is 9 with a borrow. That's a 0. 9 minus 0 is 9. There we go. 0 minus 1 is 9 with a borrow. 9 minus 1 is 8. 9 minus implicitly 0 is 9. 9 minus 1 is 8 with no borrow. So since this one has no borrow and it's 0 to begin with, we'll just leave it the way it is. Is that making any sense in base 10? Okay. So we'll go ahead and do another one in base 2. Well, let's see. How about this? We use the same thing that we had before, and to double check whether we actually did it correctly or not. So we are reusing the same numbers in this case. All right, let's try this. 0 minus 1 is, in base 2, is 1 with a borrow. 1 minus 0 is 1. Okay? 1 minus 0 is 1 with no borrow. 1 minus 1 is 0, and there's no borrow here. 1 minus 1, excuse me, 1 minus 0 is 1. 1 minus 0 is 1, no borrow. 0 minus 1 is 1 with a borrow. 1 minus 0 is 1. 1 minus 0, implicit 0, is 1. 1 minus 1 is 0. And we got our number back. Is that okay so far? Okay. So your next homework assignment, which I will assign on Thursday, is going to be, not base conversion, but I want you to do subtraction and addition in this form, just to make sure that you understand the concept of carry and borrow in base 2. Okay? It's not going to be like 30-something digits. I'll give you something that's about the same as this. Okay? Unless someone asks for 32-digit, subtraction and 32-digit, addition. And yes, if you think that you are smart and you can write a program to generate this row of carries, go ahead and do it. You don't have to do it by hand. If you want to write a program to generate the output, that's all good too. That's good with me too. It's not a challenge. Do not look at it as a challenge. The reason why I allow people to write a program to do it, as long as it is your own program and it's not somebody else's program, is because if you write a program to do this and the program works, that means you have already understood the concepts. And that's the bottom line, is do you understand the concepts? If you understand the concepts well enough to write a program to do it, that's satisfactory in my book. Okay? Is that okay? All right. All right, so that's done too. Next, the summary is already done. We know how to do addition and subtraction in base 2. Let's close that. Go back to our notes. We are basically done with this link here. The next link is starting with the architecture of the processor. In other words, the processor is really the center of everything in your computer. Why do you think I said that? I mean, obviously every component is important inside the computer, but the processor is really the center of everything. That's why it's called the CPU, the Central Processing Unit. Why do you think it is the center of everything?
Because the CPU executes code, and based on where it is in executing, it'll access the hard drive and main memory and other components as it needs it.
Exactly.
So in essence, the whole computer talks to the processor.
In one way or another, they all have to talk to the processor.
Right.
Okay, very good. So let's talk about the processor, the story of registers. Okay, and we'll start with some background information. We'll start with the ALU. Now we have just done some binary addition and some binary addition. So inside the processor, there's some transistors that influence pretty much the same thing that we just went through. If you give it a number in binary, if you give it 2 numbers in binary, it can perform addition, it can perform subtraction, and depending on your processor, some can also perform multiplication and division. So the ALU, which stands for Arithmetic and Logic Unit, can do all of this stuff really, really fast. Okay? So we can visualize the ALU to be a magical box that has 2 input and 1 output, and that's why when you go to a electrical engineering class or a computer engineering class, The ALU is a lot of times represented by kind of like a Y symbol, because you have one number coming in here, one number coming in here, and you have the output coming up, coming out from the bottom. The ALU inside the processor, it can only do computation. There's no way it can store something. It can store just the output of one calculation. In other words, it's more like a simple calculator that you can buy for $2 these days. Okay, you can add a number to another number, it displays the result, but as soon as you try to input another number, that number, the sum from the previous calculation, is gone. And that's the ALU. So obviously the ALU by itself is useful, but it cannot do everything that we need to do inside a processor. Is that okay so far? All right. On the other hand, we have memory inside the computer. You can go by memory DIMMs, dual inline memory modules, for modern computers. Is it DDR3 most of the time now? But DDR4 is available for graphics cards.
No, for graphics they use a different.
Okay, it's entirely different.
Technology.
Okay.
And it's 5.
Oh, it's DDR5.
GDDR5.
GDR5. Okay. Now, but it is still memory. Okay, and you can install lots and lots of memory in a computer. Okay, a typical computer that you buy today has probably at least 4 gigabytes of memory. Okay, which is a lot. I mean, that's a lot of storage. So that means you can store programs, you can store data, you can store lots of stuff, in RAM, in memory. So that means if the ALU is connected to memory, now we have just solved the problem with the ALU all by itself. Because memory, okay, if you look at the ALU as a simple calculator where you can just punch in 2 numbers and it will give you the answer, but there's no way it can store a prior calculation, memory is like a library. Okay, it's not, well, not a library, but it's basically stacks and stacks and stacks of binder paper that you can use to store stuff and write stuff on it. Okay, there's only one problem. The stacks and stacks and stacks of binder paper is really far away. In other words, if I want to use an analogy, using a physical analogy, the calculator, which is super duper fast, is in this classroom. Okay, I have a calculator here. You can do addition, subtraction, multiplication, and division really, really fast. But in order to store the result of the calculation, let's just say that the stacks of binder paper is in the library. Okay, so imagine this. Every time I want to do some calculation, one of you would have to run to the library to get me the 2 numbers that I'm supposed to add. Okay, somebody's going to run back to the classroom, panting, and I'll just go, oh, okay, I got a result. Now go to the library and store this on page 60,528 on that particular notebook. I give it to another person. That person's going to run out of the door, run to the library, run back, panting, and go, okay, what's next? Oh, I need the next calculation now. Okay, I need this number from page blah, blah, blah. I need this number from page blah, blah, blah. And then another person is going to run out the door to the library. What's wrong with this picture? They're not utilizing the calculator correctly, are they? Because all the time is spent what? Running. Exactly. It's running from here to the library and back. So it doesn't matter how fast the calculator is, because most of the time is spent waiting for the numbers. Okay? That's why we have registers. But before we get to that registers part, let's talk about physical limitations. The capacity of memory is huge. Okay, well, compared to the hard drive, it's not that huge, but it is big nonetheless. But it cannot be located inside the processor die. In other words, it would be nice, some people will think, if we can put 4 gigabytes of RAM on the same chip as your Pentium processor. Okay, that would be great. I mean, everything is so fast. It's kind of like having 4 gigs of cache, right? But it's not possible. Well, at least not today. Why isn't it not? Why isn't it possible? Each transistor has a certain size. To implement 1 bit of memory, you need a certain number of transistors. To implement 4 gigabytes of RAM, you need a certain number of transistors. That number of transistors turns out to be a pretty big number. So what is the problem with packing that many transistors onto a single die? Heat is a problem, okay? But there are other problems as well.
Yield problems, cost problems.
Yield problems, because your die is going to be pretty big. In other words, instead of the die being about yay big, it's going to be much bigger. That means in the manufacturing process, the chances of having a single flaw on that big die is pretty high. Because when you have a much smaller die, yes, chances of something happening will still happen. But because the die is so small, most of the dies will come up perfectly fine. It will just be a few that will have the imperfection, and you cannot use those. Okay? So there are many problems, physical limitations, as to how many transistors we can pack on a single die, and therefore, we just cannot pack 4 gigs of RAM onto a single chip. So as a result, memory is implemented as separate modules that are connected to the processor using copper traces on the printed circuit board. Modern PCs also have a north. Well, that part is not true anymore with the i3, i5, and the i7 processor. There's no north bridge anymore. Okay, but it's still the mechanism. There's still transistors in between the processor and memory that is doing the interfacing. Now, because of the physical separation of the processor and memory, now we have other problems. Okay? What do you think is the limitation? Why is it so slow to access memory? The processor is here. The memory is really quite close to the processor. I mean, they're on the same circuit board. They're not in the library. So what is the limitation?
My guess is the fact that it doesn't know exactly where it is. It has to check to find what it needs.
Not exactly. I mean, you can address memory. It's pretty easy. You just tell the memory module, I want to access location blah blah blah, and it can present the content of that address, to the processor. Yep.
Well, there's latency issues.
There's latency issues. Very good. Some people, some of you have tried to put computers together, and one of the things you want to check when you install memory is what is the latency of your memory chip. But why do we have latency? Why do we have these quote-unquote wait states? Why does the processor has to wait da 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 da? Okay, now I think the data is available. Why do you think it has to wait? Is it the speed of light? No, it's not the speed of light. We are not even close to approaching the speed of light or having that to limit how fast we can transfer content. What is it? How many people have taken physics? Yes.
Is it the conductivity issues?
Not conductivity, but you're getting very close. It's an electrical property, 2 electrical properties that is stopping information from going here to there at light speed. We know instantaneous is not possible, but we know that we are not even close to that limit. Yep. Electromagnetism is one, and then capacitance is the other one. Okay. This is not a physics class, so I'm not going to put too much emphasis on it. Basically, what they do. Okay, I'll just give you a picture so that these physics professors won't say that I'm trying to teach physics to a class like this. Ideally speaking, we want an electrical signal to be like this: crisp, clean, and very square. Okay, here it is 0, here it is 1, here it's back to 0 again. Okay, that's the ideal case. When you have inductance, which is which is magnetism, and capacitance on the line, and those are physical properties that cannot be defeated, at least not with regular copper. Your square wave becomes something that looks more like this, like that. Okay, and depending on the length of the wire, this can get worse and worse and worse. Okay, and that is why you cannot have signals traveling, well, not traveling, but you cannot send signals, at a very high rate, because otherwise it will just be merged into one kind of squiggly line, and then the other side has no idea. Is that a 0 or a 1? Okay, and that's why you have a physical limitation as to how fast you can transmit data from one side of the PCB to another side of the PCB. It's just physics. It cannot be defeated. It's there. Okay? Yep.
So what you were saying is the electromagnetic field is what's not allowing it to transfer perfectly?
If you look at current, okay, as the speed of a flywheel, okay, then you understand inductance. In other words, inherent to every conductor, every trace of your PCB is a little flywheel. Okay, it's a very tiny little flywheel. But before any current can pass, the flywheel has to spin up first. And it takes time for the flywheel to spin up. On the other hand, if you want to stop the current, the flywheel is still spinning. It takes a certain amount of time for the flywheel to come to a dead stop. That's inductance. And then there's also capacitance, which is a separate thing, but it also helps to kind of mess up the transmission. And those are physical properties of a conductor that we cannot defeat. There's no way to get around it except to make the traces shorter and shorter. All right? So because of that, there's always a delay. I mean, the actual mechanism of this, some of you will have to take electromagnetism and also electrical stuff like capacitance and stuff like that. Fun class, by the way, lots of integration and different types of math, differential equations, okay? But it's a fun class. I mean, it really helps you appreciate physics a lot more than the other physics classes. It even explains why light speed is light speed. Why do we have a constant for light speed? Okay? By the time you get to that class, you will see. All right. But anyway, as far as we are concerned, there's a limitation as quick as to how fast we can transmit data from one side or one component on the PCB to another component of the PCB. So as a result, there's a limitation as to how quickly we can move data to and from memory. Now the rest of this is really kind of old because I'm still talking about DDR2. So the bottom line is, the bottom line of this is the memory cannot feed the ALU nearly fast enough by 10 times. In other words, memory is lagging behind your processing power by 10 times. Is that still true with DDR3 and the newer processors?
It's got to be pretty close.
Yeah, because this is almost a constant all the time, because when memory is faster, the processor is faster too. And the factor of increase is the same because they're based on the same generation of technology.
So they're coming with fun.
So you're still looking at an order of 10. Okay, may not be exactly 10, maybe 7, 8, maybe 12, or something like that, but it's in the order of 10. Okay? In other words, memory is still way too slow to feed to the processor directly. Okay? And then we have opcode size. If all operations connect memory to ALU, then each instruction must be able to specify any one of the 4 billion locations in memory for a single value. Okay, what do I mean by that? Well, what do you think instructions specify? Instructions to the ALU. Remember, this is the ALU, my super duper calculator, and I'm the processor. In order to execute instructions, I need to know which instruction or which page of that huge stack of binder paper I need to access next. Remember that part? Now, when you have, let's say, 4 gigs of RAM, okay, 4 gigabytes of RAM, and it is byte addressable, how many distinct locations do I have? 4 gigabytes is about 2 to the power of 32, right? And instructions are specified in binary, right? So that means every time I want to tell one of you to get one page for me, the specification of the page number is going to take 32 bits, which is quite a number of bits already. If there are 2 sources to each operation and 1 destination in each operation, and each one requires 32 bits to specify the location, we are looking at 96 bits just to specify where I'm getting my data in and where I'm storing the output of the result, the output of the calculation. I'm wasting a lot of bits. And that's why it is also not practical to have the processor to talk to memory directly and have that as the only way to store information. So we have just described all the limitations that says, it's not a good idea to use memory all the time alone when you're using your processor, when the processor is doing processing. So the solution, obviously, is to have registers. What exactly are registers in our analogy? They're not cache, by the way, okay? Because some of you are thinking, well, maybe they're kind of like cache. No, they're not exactly like cache. Cache is transparent. Okay? In other words, from the processor or from software perspective, caching is for the most part transparent. A register is not transparent. A register is basically a storage device, a place where you can store information that is really, really close to the ALU, physically. They're on the same die. In fact, they're very close to the ALU transistors inside a processor die. So in our analogy, it's kind of like the ALU is my calculator. My registers are post-its, okay, that is surrounding the calculator. There are only about 8 or 16, very few of those. But I can get to those really, really quick. Okay? Are there any questions at this point about how registers compare to memory? Memory is all the way in the library. Registers are post-its right next to the whiteboard. Okay, a little whiteboard right next to the calculator. And I can have a certain number, a fixed number of those locations. With the i386 architecture, I cannot remember, I think there are 16 of them. Okay. Now with 16, is it 16?
Yeah, sounds right.
Yeah, I think 16 is the right, at least the right order. Now if I have 16 distinct registers, how many bits do I need to specify one of the 16 registers?
2.
4 bits, okay? Hey, 4 compared to 32, it's a big gain, okay? So that means my instructions can be a lot shorter if I can somehow limit myself to use registers as much as possible. Is that making any sense? Because if I have to use memory, I have to use 32 bits to specify one location. If I use registers, I need only 4 bits to represent to designate a single register. They're right next to the ALU. They're really fast. In fact, registers inside your processor can keep up with the ALU. As fast as your processor can produce information, can produce results, the registers can keep up with that to store the results. Not even your cache can do that. Okay? Registers are much faster compared to cache. Now, since we only have a few registers, 16 registers and 32 registers, there are some architectures with a lot more, and a lot more means 256. Okay, still a very low number of registers compared to memory capacity. So that means at some point the ALU will still have to get information from memory and to store something back into memory, because I'm going to use up all my post-its very soon. So at some point I'm going to have to say, well, I don't have any space anymore because I have used up every single post-it. And I need to store this somewhere so that I can free up some of the registers. I can do some more calculations. So eventually, you will still have to send someone to the library to write to memory or to read from memory. But this will help the processor keep busy most of the time, because most of the time it's going to get the source and the destination from the registers. And of course, the impact to the instructions is a twofold thing. Instructions need to be able to specify memory locations and registers, and they're two separate things on most architectures. In other words, if you want to specify memory, it is one instruction. If you want to specify registers, it's another instruction. Okay? Now this is important. We'll come back to this later. That memory is not register. They're very distinct things. Some architecture allows an instruction to specify a mixture of registers and memory. In other words, you can specify something to come from register and something to come from memory. Instruction is in quotes because this I'm referring to the mnemonics as opposed to opcode. Okay, mnemonic is basically a text representation so that we can remember which instruction we are talking about. The opcode is the actual binary bit pattern representing an instruction to the processor. Okay, I'll clear this up and then we'll end this lecture. Mnemonic is basically a name so that we can remember the instruction more easily. Opcode, on the other hand, is useful to the processor because it's just a binary bit pattern to specify the operation. What this means is the same mnemonic, let's say multiply or add or subtract, can correspond to many, many different unique opcodes because one opcode can say, okay, get both operands, the source of information, from memory and store the result back into memory. But the mnemonic is still saying subtract. Another instruction, another opcode is saying, I want to get this from a register, get that from a register, and store the result in a register. It is still a subtraction operation, so the mnemonic is still subtract, but the opcode can be entirely different. Are we doing okay with this? Because the mnemonic is seeing things from our perspective. What does it do? Subtract, add, compare, jump, go to, and so on and so forth. But opcode is seen from the processor's perspective, a unique bit pattern to specify a unique way to process something. Where am I getting the information from? Where am I storing the information? Okay. And it would be nice to at least mention these terms. CISC is complex instruction set computer versus RISC, which is reduced instruction set computer. The i386 instruction set, which is what we'll be using in this class, is actually a CISC. On the other hand, I'm teaching the class as if it is a RISC in some cases. In other words, there are certain instructions that can combine the effect of multiple instructions. So instead of using those instructions, I would actually explain how to use simpler instructions to implement a CISC instruction. Okay. We're actually running out of time, but since we're on this topic, and I think some of you already know the answer to this question. Why do we have RISC? I mean, isn't it better to have instructions, a single instruction that can do more? I mean, instead of having to rely on multiple smaller and simpler instructions to get the same thing done?
When you're implementing the design of a microarchitecture, one of the design goals is to make it as simple as possible because simple usually means more efficient.
More efficient, that's right. Now, what is the one thing? Okay, let's think about this, and and I'll let you guys go. What do you think is inside my cell phone? Is it a CISC processor or a RISC processor?
I believe it's right.
It's a RISC processor. Now, why do we have a RISC processor instead of a CISC processor inside the cell phone?
Power.
Power? Well, but why do you think a CISC processor is more of a power hog? Why does it consume more power?
It's more complex. It's more complex.
There are more transistors, right? Because instead of having just maybe 80 instructions, it has hundreds of instructions. If you have hundreds of instructions, you have to have all the silicon, all the transistors to deal with each and every one of those instructions. And all those transistors will consume power. Okay? Whereas a RISC, on the other hand, does not need all that transistor. But there's one more reason why a CISC is better. I mean, a RISC is better. A RISC processor is better. Which one do you think has a bigger die? A bigger physical presence? A CISC, right? So if I have a wafer, basically the silicon, that makes the die, you make it and then you cut it up into dies. But when they first made it, it's called a wafer. From the same wafer, I can make more RISC processors than I can make CISC processors. So that makes each CISC processor cheaper than a CISC processor of the same capability. Okay. But the price I'm paying is that I have to use more instructions. In other words, that's a price that to be paid by the programmer, not in terms of the manufacturing cost of the device. Who writes programs in assembly these days? Not too many people. So who's actually paying the price? The compiler. Do we care? Do we care the compiler now has to crank up 6 instructions instead of 2 to do exactly the same thing? We don't care. That is why we use CISC. That's why we use RISC processors in applications like these instead of a CISC processor.
I was just going to mention that the reason that CISC processors are used in more complex computers is backwards compatibility.
Exactly. It's all because of backward compatibility, which is really kind of strange because if you look at Linux, a different architecture is not a problem. A very small percentage of the Linux kernel is written in assembly because there's no way to get around that part. The rest of it, which is more than 90%, is written in C. Linux has been ported to non-physical processor. In other words, they just release the specifications of the processor and you can run it in an emulator, and somebody already ported Linux to that platform before the first chip was made. So backward compatibility should not really be an issue. You can recompile everything. Just ask anyone with Gentoo. Right?
Yeah.
And I guess Microsoft still has not learned the trick of recompiling stuff, because it's still way tied into the i386 architecture. But that's a story for another day, for Thursday. I'll see you guys on Thursday. I will go to the lab later today, so if you have any questions, I'll be in the lab.